Dear students, today we are going to discussion about the one more important concept, that electric field due to the system of charges. Electric field at a point due to the system of charges. For the last class that we have been discussed about electric field concept, what is meant by that electric field, and also electric field is a vector or scalar. That electric field is a vector quantity because it should have the magnitude as well as direction. And one more important concept in this case, in that electric field or electric field intensity. So electric field at a point due to the point charge, that E equal to 1 divided by 4 pi epsilon naught Q divided by R square. That particular derivation that we have been derived. Now, we must able to discussion about electric field at a point due to system of charges. Here, number of point charges are there. What is the electric field? The previously electric field at a point due to the point charge. But in this case, what is that electric field due to system of charge or multiple charges? What is the electric field at this particular point? Let us consider in this case Q1, Q2, Q3, Q4. These are all the point charges placed in an air medium whose position vectors, say R1P, R2P, R3P, R4P from point P. So far, with reference to this, it's a very simple thing. This is the point P. These are all number of point charges. Say multiple charges or system of charges. What is the electric field at this particular point P due to all these system of charges that we are going to find out. It is similar to the previous that expression. There, electric field at a point due to point charge, that expression that already we know that E equal to 1 divided by 4 pi epsilon naught Q divided by R square. It's a general expression. Unit vector that R, that's also. But in this case, that point P, I want to find out that electric field at this particular point due to all this system of charges. So far, the electric field due to the system of charge, how to define? It is defined as there must be some force experienced on unit test charge at this particular point P without disturbing these original position of the charges. All these original positions. Without disturbing this, we must able to place that one test charge here. The test charge you may able to take unit positive charge also that you may able to take in this case. See, exactly the same thing. This is the Q1 point charge. This is the point P. You may able to consider here the plus the test charge. Unit positive charge also the test charge. Between these two, separated by distance is R1P. So, what is the electric field between these two? What is the electric field between this, say, point charge as well as this test charge or unit positive charge? What is that expression? So, that electric field E1 at this particular point P due to this charge Q1 at a distance is R1P is, say that E1 equal to 1 divided by 4 pi epsilon naught Q1 divided by R1P square into, say that R1P unit vector, where this R1P is the unit vector in the direction of Q1 to P, in the direction of Q1 to P. In this point P, we have been placed the unit positive charge also, the test charge also. So that R1P is the distance between those two. Isn't it? Exactly the same way. You must be able to take this is also the Q2 point charge. And here the test charge that we have been placed, separated by distance is R to P. Again, the electric field at point P due to this charge Q2 is, say what now? E2. So that E2 equal to 1 divided by 4 pi F naught Q2 divided by R to P square R to P. Say this is the unit vector. As usual, it is along the direction of Q2 to P, and then R to P is the distance between them. Similarly, say for Q3 and Q4, Q5 and so on up to Qn. So far, say electric field that En equal to 1 divided by 4 pi F naught Q1 N divided by R, say Np square Rnp unit vector. This is the simple expression. As already we studied about the principle of superposition of electric forces. Exactly the same way, we can able to analyze that principle also we have been used in this case. So far, that what we have been studied for the previous class. Now, ee munche principle of superposition of electric forces ಬಗ್ಗೆ ನಾವು ಕಲಿತುದುಂಟು. Total force equal to F1 plus F2 plus F3 plus F3 plus F4 so on up to that Fn. That is the principle of superposition of electric forces that we have been studying. Exactly the same way, we can able to apply here also by the superposition principle. In this case, what happens now? There must be some several charges. Ultimately, what we suppose now? That electric field or electric field intensity at that particular point, electric field intensity at that particular point, say point charges is the vector sum of, say that's each charges individually in that absence of that other charges. Ultimately, what we suppose take the electric field E at that particular R due to the system of charges is vector sum of that individual, say that electric field intensity. So with respect to that particular charge, that E1 plus E2 plus E3 up to that En. Just you substitute those values in this, say 104 by F naught, Q100 by R1P square, R1P unit vector, up to 104 by F naught, Q100 by, say that R1P square and Rnp unit vector. In general, that I can write equal to 1 divided by 4 pi F naught summation of Qi divided by that R1P square, R1P unit vector, where I equal to 1 to N. This is the general expression, that is what we supposed to know. General expression for electric field at a point due to, say, multiple charges. Apart from this, that electric field in these particular considerations, we go for the physical significance of that electric field. The next concept is what we call it now, say physical significance of that electric field. Of course, we know that physical significance of electric field. But you try to understand what is electric field and say what is electric field at a point due to point charge. With reference to that all, we can able to derive the expression for electric field due to system of charges. In general, let me know that sometimes they be able to ask what are the physical significance of electric field. It's a simple thing. See, the concept of the electric field, it was introduced by that Faraday. He gave us some more the idea about the electric field. Of course, that electric field is a vector quantity. It should have both magnitude as well as direction. So far, it is the vector quantity. And also, in the electrostatic concept of the electric field, it is not really necessary, but it is convenient only. So for the next one, electric field is a characteristic of system of charges, and also it is independent on test charge. It should be independent on test charge. Even also the previous class that have been discussed. So that electric field, it is depending on what the point charge and also the distance, but it is not depending on the test charge. It is independent on the test charge. That's what. And also the Coulomb force between 2 point charges encourages us to think in terms of action at a distance. Of course, the Coulomb's law, that concept, often we are supposed to use even also to derive that explanation of the electric field concept. The field is introduced as particularly intermediate between the charge. Means, of course, the charge and field and charge, that particular concept that we have been explaining. So far, with reference to that all these things, this is the most important concept, the electric field strength. Sometimes we may be able to call what is meant by that electric field. It is also the same thing. What is meant by that electric field intensity? That is also the same thing. Electric field strength, that is also the same thing. Electric field intensity, or electric field strength. All of that the same. That should be denoted by the letter E. But you have that idea about that electric field concept now. As usual, you know that. Say some force experienced on unit positive charge. That's electric field strength or that electric field. So far, after knowing the concept of this electric field and these more derivations. So, as I told, electric field at a point due to the point charge, there is also one derivation. For the board examination point of view, 3 marks question, already they have been asked in the examination. And this one also for 3 marks question, say for this derivation, we are going to concentrate this. Especially all these supposed to use to solving the numericals, this particular concept that we have been used now. So the next one, the concept, that's what electric field lines or electric lines of force. That will discussion now. See now, that electric field lines are electric lines of force. As usual, we know that Michael Faraday introduced the concept of these electric field lines. What actually mean by these electric lines of force? So for the examination point of view, these field lines, about these field lines and the properties of electric field, this concept they may be able to ask in the examination. Many years they have been asked for 3 marks questions based on these electric field lines as well as properties of electric lines of force. So far, say these electric lines of force, nothing but what? Say the path, say a unit positive charge or test charge moves or tending to move. For example, say that it is the unit positive charge, or you may call it now the test charge. Say the test charge moves or tending to move. Say moves or tending to move. Say path along which the small test charge, may call it a small test charge, say moves or tending to move, say that is nothing but electric lines of force. These electric lines of force, they may be straight line. Electric lines of force, they may be straight line, or they may be curved lines also. When these electric field lines, they must be straight line. If suppose, say that electric field is due to an isolated point charge, then electric field line is a straight line. Of course, it's a straight line. Only when, say that electric field due to an isolated charge, a single charge, so the field lines will be the straight line. If suppose, say that electric field line, so that electric field is due to 2 or more number of charges, then electric lines of force are curved. Electric lines of force are curved. More than 2 charges, if they are, obviously there must be the curved lines. That is also one of the important concepts. In general, we know that if that electric field is that uniform, electric field lines will be, say, the straight line parallel to each other. That electric field lines, electric field will be that non-uniform, say, these electric field lines will be that curved lines. If suppose these electric field lines will be curved, then what we are going to concentrate in this case? We must be able to draw the tangent. That tangent, it gives the direction of these electric field lines. That gives the direction of electric field lines. But in this case, that we are going to discussion, that one of the important concepts, how that electric field lines will be more concentrate. Where that electric field lines will be more concentrate, say that particular concept that I would like to explanation here. Of course, say that electric field will be that more, say that electric field lines will be more concentrate. For example, this is the test charge, that's a Q charge. So, these are all the electric field lines. Electric field lines. Say, these are the field lines. These are the field lines now. So far, see, in this case, that gives what? The direction. This arrow, it gives the direction of electric field lines. See, then what happens to here? If they are all, yes, this is what now that arrow is. That arrow, it gives the direction of this, say, electric field lines. See, here, strong electric field lines will be more. Strong electric field lines will be more. See, if the field lines, they are away from this charge, so far in this case, what now the field will be weaker one. Field will be weaker. I mean, electric field will be weaker. So, this we can able to analyze here. This is what now? See, that's magnitude. If they are very close to this charge, so that electric field will be more concentrate, more strength here. Strong electric field in this case, so that the magnitude of these lines, obviously, say it should be more. If they are moving away, their magnitude, the arrows, they are smaller. Means because in which the electric field will be, say, weaker one. Now, ಇದು ಚಾರ್ಜ್ ಇದೆ, ಇಲ್ಲಿ ಚಾರ್ಜ್ ಇರೋದ್ರಿಂದ ಮ್ಯಾಕ್ಸಿಮಮ್ ಸ್ಟ್ರಾಂಗ್ ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ಇರ್ತದ. ಯಾವಾಗ ಸ್ಟ್ರಾಂಗ್ ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ಇರ್ತದ, ಅಲ್ಲಿ ಎಲೆಕ್ಟ್ರಿಕ್ ಲೈನ್ಸ್ ಆಫ್ ಫೋರ್ಸ್ ಮೋರ್ ಕಾನ್ಸಂಟ್ರೇಟ್ ಆಗಿರುತ್ತೆ. ಇಲ್ಲಿ ಮೋರ್ ಕಾನ್ಸಂಟ್ರೇಟ್ ಆಗಿರುತ್ತೆ. ಯಾವಾಗ ಸಿ ಲೈನ್ಸ್ ಆಫ್ ಫೋರ್ಸ್ ಅವೇ ಫ್ರಮ್ ದಿಸ್ ಚಾರ್ಜ್ ಆಗಿ, ಅಂದ್ರೆ ಇಲ್ಲಿಂದ ದೂರ ಹೋಗ್ತಾ ಹೋದಂಗ ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ವೀಕ್ ಆಗ್ತಾ ಹೋಗತ್ತೆ. ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ಸ್ಟ್ರೆಂತ್ ವೀಕ್ ಇರತ್ತೆ. Yes, in these particular considerations, we must able to discuss here the dependence of electric field strength on the distance and also its relationship, the number of field lines. This is the basic thing that I would like to discuss. As I told here, this is the charge as usual, that QB, that charge. In this charge, what happens now? Nearby this charge, electric field, the region, the electric field will be more strengthened one. ಯಾವಾಗ ಈ ಪಾಯಿಂಟ್ ಚಾರ್ಜ್ ಇರ್ತದ, ಇಲ್ಲಿ ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ಜಾಸ್ತಿ ಇರ್ತದ. ಸೊ ದ ರೀಜನ್ ಆಫ್ ದಿ ಸ್ಟ್ರಾಂಗ್ ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್. ಯಾವಾಗ ಚಾರ್ಜ್ ದಿಂದ ಈ ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ಲೈನ್ಸ್ ದೂರ ಹೋಗ್ತಾವು, ಸೇ ಅವಾಗ ಈ ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ಏನಪ್ಪಾ ಅಂತಂದ್ರೆ ವೀಕ್ ಫೀಲ್ಡ್ ಇರುತ್ತೆ ಅಂತ ನಾವು ಹೇಳ್ತಾ ಹೋಗ್ತೀವಿ. Of course, this is how the dependence of electric field strength on the distance and also its direction to the number of field lines. So far, in this case, this is a charge. For example, you may be able to analyze about this particular concept. For example, in the two-dimensional that we have been taken, say this is the point O and this is the AB. See, it makes an angle delta theta. This is the region, that's the length. So far, there's some curve here. Its length is delta L. So this angle subtended delta theta equal to delta L by R for that two-dimensional. So far, this is the 3D in a three-dimensional. What happens now? This is the charge Q and this is the surface area. So far, this surface area and this it is in the strong field, electric field, and this is what now? That weaker field. So, this is the surface in a three-dimensional. Just you imagine, it's in a 3D. Nimagottu, three-dimensional, 3D. So far, in this case, this is the surface area. So far, this distance is that R1, we call it now, in general that R. So, this is the surface area and it makes an angle that is the delta omega. So, this angle delta omega, according to this, that what we may be able to get, say delta omega equal to delta S divided by R square. In general, that what we came to know that. So far, with reference to this, I would like to analysis in this case. So far, this is the solid angle. This solid angle is delta S divided by R square. For example, say here that these are all the electric lines of force. So far, these electric lines of force will be more because it is a very strong region of electric field. So far, this is the electric, in this electric lines of force, they are weaker. Weak field, of course, they are almost, the distance would be more here. Here, very closely associated, but here they are away from. That is what in these particular considerations. How exactly these particular concept that I would like to analyze here. Apart from this, let us discussion about most important one is say general properties of electric lines of force. That are also I will discussion here. General properties of electric lines of force. That is also one of the important thing. For the board examination point of view, always they have been asked for say 3 marks question. Write the general properties of electric lines of force. See, these electric lines of force, electric field lines always directed away from the positive charge and they originate from the positive charge and terminate at the negative charge. For example, this is the positive charge. Electric lines of force originate from this positive charge, say terminate at that negative charge. All these say electric lines of force originate from this positive charge and terminate at negative. If it is the negative charge, electric lines of force, they must be terminate at this negative charge. It is one of the important concepts here. So for these electric lines of force, they are normal to the surface of the conductor if the conductor should be in equilibrium conditions. Electric lines of force, they must be normal to the surface of the conductor. That conductor should be in an equilibrium condition. So far, these electric lines of force cannot pass in through the conductor. For example, this is the conductor. So far, in this conductor, electric lines of force cannot pass in through this conductor. So it's wrong. See, electric lines of force always say They are like this in this case. These electric lines, of course, they are imaginary lines. What we supposed to say? It's not at all. We must be able to say electric lines of force. So far, with reference to this, let me take one of the important concepts based on this. Electric lines of force cannot pass it through the conductor. It means what I said, electric field lines inside the conductor is zero. Field lines inside this conductor is zero. And one more thing, electric field lines, they never intersect each other. Electric field lines never intersect. For example, this is also that one electric field line, this also that electric field lines. They never intersect each other. It is not possible. Because at the point of intersection, you must be able to place that 1 coulomb charge. That is the unit positive charge that may be able to place at this point of intersection. It makes this unit positive charge moves in both the directions. It moves both the directions simultaneously. But it is impossible. If it is impossible, so the electric lines of force never intersect each other. So that electric field lines do not form that any closed loop. They do not form that any closed loop. So these electric field lines at the region of stronger electric field, more number of electric field lines will be concentrated. In that weak, say less number of electric field lines will be formed. Of course, if it is a positive charge and it is a negative charge, see how they originate. Of course, like this. Electric field lines must be originate like this. Originate and terminate at that originate at positive, terminate at negative. See that one more thing. If it is a positive charge and this one is that positive charge, what happens? Say that pictorially that you can able to representing this. This is what more. Because both are same charges, ultimately there must be some, say, repulsion will be taken place. This is also one of the important concepts. If suppose that negative, this is the negative and this is also the negative. What happens? How to represent it? This pictorial you can able to represent it like this. So far here, repulsion will be taking place between this. Again we concentrate about the properties of electric charges. Okay? These are all most important concepts for properties of electric field lines. For the board examination point of view, you must concentrate, write the general properties of electric field lines. So far, 3 marks questions. Many times they have been asked. And based on this concept for the competitive examination, one question is compulsory based on these electric field lines. You try to understand the properties of these electric field lines. Okay?